The Space Bermuda Triangle, South Atlantic Anomaly. Imagine drifting alone in the inky black, Earth's blue curve glowing beneath you, until, without warning, your instruments flicker, guidance systems hiccup, and alarms whisper of an unseen threat. This is the South Atlantic Anomaly, a spaceborne Bermuda Triangle where our planet's magnetic shield dips so low that radiation surges can send satellites into spasms and even rattle the International Space Station. Since the 1970s, every spacecraft that dares cross this oval scar above South America has risked unexplained resets, corrupted data, or total system shutdowns. When NASA's EPS-1 satellite first rebooted itself in 1972, no one knew why. By the 1990s, engineers had baptized the region the South Atlantic Anomaly, and its reputation only deepened as it drifted, split, and ballooned in size, challenging mission planners and raising questions about Earth's very core. At the anomaly's heart lies a sluggish patch of dense, iron-rich rock deep beneath southern Africa. Dubbed the African Large Low-Velocity Province, this blob warps the convective currents that churn Earth's molten outer core. The result? Our inner Van Allen belt bulges southward until it dips to within roughly 200 kilometers of the surface, half as far as anywhere else. Passing through that weakened field subjects satellites and astronauts to high-energy particles that would normally be deflected far above. Thanks to ESA's Swarm constellation, 3 magnetometer-equipped satellites launched in 2013, we now watch the SAA creep northwest at about 10 kilometers per year, split into twin lobes, and expand by nearly 20% over the past decade. One lobe edges toward Brazil's coast, the other drifts over the South Atlantic. Every new bulge means fresh orbital paths exposed to dangerous radiation doses. Why should you care? Because each energetic particle that pierces a satellite's skin can flip a bit in its memory, corrupt sensor data, or even fry circuitry. Weather monitors, Earth observation platforms, GPS satellites, they all shut down non-essential systems during SAA crossings, trading vital science hours for safety in an 8-minute transit. On the ISS, astronauts suspend experiments, trading groundbreaking research for sheer survival. Yet even these precautions aren't foolproof. In 2018, NASA's NICER X-ray telescope aboard the station suffered sudden data blackouts when its detectors were overwhelmed by charged particle bursts. And the Goce gravity mission, designed to skim the edge of space, logged mysterious reboots as it skimmed the anomaly at a mere 255 kilometers altitude. Each glitch underscores how this magnetic pitfall can undermine the most rigorously tested technology. Beyond these operational headaches, the SAA offers a window into Earth's deep interior and a possible harbinger of our planet's magnetic future. Some geomagnetic models suggest that the anomaly's growth could signal the early stages of a field reversal. During past flips, Earth's magnetism weakened by up to 90%, leaving us vulnerable to cosmic radiation that could disrupt power grids, satellite networks, and even airline communications. That looming prospect has scientists racing on multiple fronts. In 2024, a team at the University of Bristol used ultra-high-pressure experiments to show that Africa's dense province conducts heat far differently from surrounding rock, validating theories that it seeds surface-level magnetic oddities. Meanwhile, computational geophysicists are weaving real-time swarm data into dynamic geomagnetic forecasts, aiming to warn satellite operators and power utilities of impending radiation storms. Engineers, too, adapt. NASA's upcoming Geospace Dynamics Mapper will boast hardened electronics built to withstand prolonged exposure, and ESA's next Earth Explorer missions will integrate onboard magnetic shields and AI shutdown protocols that learn to anticipate particle surges. Commercial small-sat constellations now favor modular designs, so damaged components can be swapped out in orbit, because in space, redundancy is the ultimate insurance policy. Still, for all the science and safeguards, the South Atlantic Anomaly retains its aura of the inexplicable. It's a scar on Earth's magnetic canvas, a living reminder that our planet is a dynamic, pulsing engine whose hidden depths ripple into the void. Every time a satellite skims through that radiation-soaked oval, it writes another chapter in a story that began billions of years ago, when molten iron first set our world ablaze with a magnetic heartbeat. So next time you check the weather on your phone, or marvel at streaming images of Earth's auroras, spare a thought for the silent triangle of peril moving beneath your view. In the dark heart of the South Atlantic Anomaly, the boundary between our planet's molten core and the cosmos blurs, testing our high-flying ambitions with the very forces that forged this world. Where will our next journey take us? Subscribe, ring the bell, and join us as we unearth another forgotten marvel.